If you recall from the previous section, we talked about random variables. In this section, we're going to talk about something called a binomial random variable, which comes from a binomial distributions, which comes from a binomial experiment. So here, binomial experiment, how do you identify if an experiment is a binomial experiment? And this is really important. So here, a binomial experiment is a probability experiment that satisfies the following requirements. So you want to check that all of these 5 requirements are satisfied. If they are, then you could just say that this experiment is a binomial experiment. If just one of them fails, then you could say that this is not a binomial experiment. So let's just go over them. First thing you want to check is that the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial, and the number of trials is denoted by the letter n. So you want to identify what is your trial in your experiment, and once you find that, you just call it n. Each trial has 2 mutually exclusive outcomes, a success outcome and a failure outcome. So again, what does mutually exclusive outcomes mean? It just means that these 2 events can't occur at the same time. For example, a person can't win a lottery and lose a lottery at the same time. The probability of success is the same for each individual trial of the experiment. The trials are independent, which means that the outcome of one trial does not affect the outcome of the other trial. That's just the definition of independence. It just means that the outcome of one trial doesn't really affect the outcome of any of the other trials. The random variable x is represented by the number of success that occur. There's a couple of notation that I want you to get really familiar because we're going to use these a lot. So again, the number of trial is denoted by the letter n, and the probability of success is denoted by the letter p. And so the probability of failure is just 1 minus p. So let's do a couple of examples. So here you want to determine which of the following experiment is qualified as a binomial experiment. For those that are a binomial experiment, we want to identify the number of trials, the probability of success, the probability of failure, and the possible value of the random variables. So let's look at the first example, or the first experiment here. So an experiment in which a basketball player who historically missed 20% of his free throw is asked to shoot 3 free throws, and the number of free throws missed is recorded. So if we remember that from the list of requirements here, we have to check if all of these are satisfied. So first thing we want to know is that, is there some sort of fixed number of trial? And if you see here, there is 3 free throws. They asked him to shoot 3 free throws. So here, I'll just put 1. There are n equals 3 trials. There are 3 trials. So there is a fixed number of trials, which is 3. And I just call it n equals 3. Next is that we want to see if there's like 2 mutually exclusive outcomes. And there actually is. So I'm just call this 2. There are 2 mutually exclusive outcome. And what are they? Well, miss the free throw. In this case, this is marked as a success. So just the thing you want to note is that a success, quote unquote success trial, doesn't always mean a good thing. It could also sometimes be a bad thing. So like missing a free throw could be considered like bad, but in our experiment, this is our success event. And then making, or I guess make the free throw is considered a failure. And these are two mutually exclusive events because you can't miss a free throw and make a free throw at the same time. So we're okay. Another thing is you want to check if these trials are independent of one another. And they are. The trials are independent. So how do I know? Well, you kind of see that each free throw or each trial doesn't really affect the outcome of the next trial. So there should be independent events. Number 4, you want to see if there's a probability of success. Here, we know that this basketball player historically missed 20% of his free throw. So we actually know the value of the probability of success here. So here, the probability of success is 0.2. So this should be a binomial experiment. So we're okay. The last thing I know, I said like the random variable x represents the number of success that occur. Which x is just like the label. I guess x is just the miss the free throw, quote unquote. I guess that represents our x. But so this is a binomial experiment. Let's consider the next experiment. So an experiment in which 3 marbles are drawn without replacement from a bag of 10 marbles, of which 3 are red, 2 are yellow, and 5 are green, and the number of green marbles drawn is recorded. So here, let's just draw a quick diagram. So here we have a bag, and we have 3 red marbles, 2 yellows, and 5 green. First, we want to see if is there like a fixed number of trial here. Well, they said they are drawing 3 marbles here. So I guess our fixed trial is 3. So n is 3. However, we are drawing without replacement. So what does that mean? It means that, let's say I pick a yellow marble on the first try. I don't put it back, I actually just leave it out. It's without replacement. So we have fewer or less marble on one trial than there is on the second trial. Or other way, there's a few marbles on the second trial than there are in the first trial. So what does this mean? Well, if you remember, without replacements means that the probabilities or these events are not independent of one another. Each trial influence the next trial. And that's a bad thing because that kind of gives you an idea that, so notice that for 2, the trials are not independent. Since we are not replacing the marbles after drawing them, right? Because each trial does influence the next trial. If I were to pick green on the first trial, then there will be less green marbles on the next trial. So they are not independent of one another. Since they're not independent, so we can conclude, so we could say, thus, this is not a binomial experiment. Cool. Now let's consider this experiment. An experiment in which a basketball player who makes 90% of her free throws is asked to shoot free throws until she misses, and the number of free throws attempt is recorded. So here, off the bat, is there some sort of like fixed trial? Well, they ask her to shoot free throws until she misses. And we don't know when that is. It could be the first 5 shots, it could be the first 10 shots. So we have no clue. So here there's no fixed trial. Since there's no fixed trial, thus this is not a binomial experiment. This is not a binomial experiment. Okay, let's do a couple more examples. So here we want to determine our p, n, and x for the following binomial experiment. So here we're already given that these experiments are already a binomial experiment. What I'm asking you to do is to identify what is our p, and here this is just our probability of success here. N is just the number of trials, and here x is just the possible value of our random variable. Okay, so the reason why I want you to do a couple more practice on identifying our p, n, and x, because we're going to actually use them a lot throughout this whole section. According to the medical journal, 9% of the population has blood type B. Suppose we choose 18 people at random from the population and test the blood type of each. What is the probability that three of these people have blood type B? So here, 9% of the population has blood type B. We kind of see that, or we kind of like, they give us a hint that our probability of success is 0.09. Let me write that better. Since we're choosing 18 people at random from the population, our number at trial here, or our n, is 18. Since we already know what our probability of success, we could calculate the probability of failure, which is 1 minus p, or 1 minus 0.09, which is 0.91. It's asking us what is the probability that three of these people have blood type B. So here our possible value of a random variable, x, equals 3. So we're not going to compute this just yet, the probability that three of these people have blood type B. That's going to be later on into this section. So right now I just want to practice how to identify our p, n, and x, because a lot of people have a little bit trouble with that. So let's consider this problem. The Pew Research Center reported in a recent year that approximately 30% of the US adult owns a tablet computer such as an iPad, a Samsung Galaxy Tab, or a Kindle Fire. Suppose a simple random sample of 15 people is taken. What is the probability that exactly four of the sample people own a tablet? So here, since we know that approximately 30% of the US adult owns a tablet, this kind of gives us a hint that our probability of success, P, is 0.30. Since we already know the probability of success, we could automatically compute the probability of failure, which is just 1 minus p. So this will be 1 minus 0.30, which is just 0.70. Now we want to look for our n, or our fixed number of trial. Since since they say that suppose a random sample of 15 people was taken, so here the number 15 is our number of trial. So here n is 15. They want to know what is the probability that exactly 4 of the sample people owns a tablet. So here x is 4. Okay, so again, right now we're just identifying what is our p, n, and x. P, n, and x. It's because we're actually going to compute these probabilities right now. So a binomial distribution is just the outcome of a binomial experiment. So the proper definition here is that the outcome of a binomial experiment and the corresponding probability of these outcomes are called a binomial distribution. And one thing you want to note is that these binomial distribution is just a special type of probability distribution. So how do we compute these probabilities? Well, the probability of obtaining exactly x success in n independent trials of a binomial experiment is given by this formula here. So here, p of x is just equal to n choose x times p to the power of x times 1 minus p to the power of n minus x, where n is the number of trials, p is the probability of success, and x is just the possible value of our random variables. And this is kind of the reason why we've done so much practice about identifying what is our n, p, and x, because once we know these values, we could compute the probabilities. So here, let's consider the same example that we did earlier. So from this example, we figure out that our n, number of trials, is just equal to 18. And our probability of success p is equal to 0.09. Since they're asking what is the probability that 3 of these people have blood type B, our x is equal to 3. So let me write down the formula again. So p of x is equal to n choose x, p to the power of x, 1 minus p to the power of n minus x. So here is asking what is the probability that 3 of these people have blood type B. So here x is 3. So now we could just fill in the missing pieces. So this is just equal to 18 choose 3. This is times 0.09 to the power of 3 times 1 minus 0.09 to the power of 18 minus 3. So this will be equal to 18 choose 3 times 0.09 to the power of 3 times 0.91 to the power of 15, because 18 minus 3 is just 15. So here, 18 choose 3, we already know how to compute this from section 4.4. So recall from 4.4. So we're able to do this. So just a little reminder here, I'll just put it in the side. 18 choose 3 is 18 factorial divided by 3 factorial times 18 minus 3 factorial. And you can just put this in your calculator. So this is just 18 factorial over 3 factorial times 15 factorial. But let's say like the calculator is just giving you an error. So you could rewrite this to make it a little bit easier. It's just 18 factorial you could rewrite this as 18 times 17 times 16 times 15 factorial divided by 3 factorial times 15 factorial. Now notice that this here divides to 1, 15 factorial over 15 factorial. So we could write this as 18 times 17 times 16 divided by 3 factorial, which is a lot easier to compute. So if you put this in your calculator, this is just going to be 816. Now that we know this value, we could just plug it back into here. So this is going to be equal to 816, because I got this computed to this. So this is times 0.09 to the power of 3 times 0.91 to the power of 15. So if you put this in your calculator, if you put all of this in your calculator, this should give you the value of 0.1446 if you round to 4 decimal places. So in words, the probability that 3 of these people have blood type B is 0.1446, or if you like percentages, I guess you could say that 14.46%. The great thing about probabilities with binomial experiments is that since we know each trials are independent, that comes with some of the properties, special properties with probabilities. So here, binomial commutative distribution functions, to find the probability of getting like less than or equal to x success out of n trials by hand, you need to calculate each individual probability using the formula above and add them. So what does this mean? Well, it's kind of similar like what we did in section 5.1. Since each trials are independent, the probability of A or B is just equal to the probability of A plus the probability of B. You're adding each individual up, each probability individually. So let's do an example here, and it'll probably be a little bit more clear. So here, we already discussed this example. The Pew Research Center reported that in recent year that approximately 30% of the U.S. adults own some sort of like tablet, like an iPad, a Samsung Galaxy, or a Kindle Fire. Suppose a simple random sample of 15 people is taken. We want to use the binomial probability distribution to find some of the probabilities. So here, we already know that n is equal to 15. The number of trials is 15. And the probability of success here is just 0.3. The only thing that's changing is our x value here. So that's going to change for each individual question. So for example, number 1, find the probability that exactly 4 of the sample people own a tablet computer. So here is asking you, what is the probability that exactly 4 of the people own some sort of tablet? Well, from the little formula that we just did here, we can compute this because we know our n and we know our p. And we also know what our x value is for this specific example. So this is going to be equal to 15, choose 4, 0.3 to the power of 4 times 1 minus 0.3 to the power of 15 minus 4. And again, all I'm doing is plugging the values that we know into the formula. So let's consider this one here. 15 choose 4. Again, if you forgot how to compute this, go back to section 4.4 and it should be there. So this is just 15 factorial over 4 factorial times 15 minus 4 factorial times 0.3 to the power of 4 times 0.7 to the power of 11, because 1 minus 0.3 is just 0.7 and 15 minus 4 is just 11. So if you actually put this in your calculator, this is going to be, well, let's do this first. If you computed this correctly, this will be 1,365 times 0.3 to the power of 4 times 0.7 to the power of 11. And this will be 0.219. So the probability, in words, the probability that exactly 4 of the sample people own some sort of tablet is going to be 0.219 or 21.9%. Okay, how about number 2? Find the probability that fewer than 3 of the people own some sort of tablet. Fewer than 3, huh? So what does fewer than 3 means? What does this mean? Well, then this is just 0, 1, and 2. Since it's saying fewer than 3, 3 is not included. So that's why it's just 0, 1, and 2. So all it's asking you is what is the probability that 0 or 1 or 2 people own some sort of tablet. So again, since these trials, it's kind of like what we did with 5.1. Since we know that these trials are independent, this is just going to be the probability of 0 plus the probability of 1 plus the probability of 2. And let me put this in different colors just to make it a little bit easier. And let's make this green. So here we want to compute this. So this will be 15 choose 0 times 0.3 to the power of 0 times 1 minus 0.3 to the power of 15 minus 0. Oh, let me make this red. So this here is just this computation. So plus, make this blue, 15 choose 1 times 0.3 to the power of 1 times 1 minus 0.3 to the power of 15 minus 1 plus, make this green, 15 choose 2 times 0.3 to the power of 2, 1 minus 0.3 to the power of 15 minus 2. So all I'm doing is I'm computing each of these probability individually and then adding them up. Because each trials are independent, I could use this rule. So if you do this correctly, this is going to be equal to 0.0047 plus 0.0305 plus 0.0916. Yeah, I'm cutting a couple steps just of time, but I kind of expect you to kind of walk it through. So if you add all this up, this should be 0.127. Yeah, so the probability that fewer than 3 of the people own some sort of tablet is 0.127 or 12.7%, if you like percentages. How about this one? This one's a little bit tricky. So you want to find the probability that more than 1 person owns some sort of tablet. So what does more than 1 person mean? So let's put this in words. The probability that, say, more than 1 person. Since we talk about more than 1 person, this is talking about like 2 people or 3 or 4 all the way up to 15. Because the reason why we go up to 15 is because there are 15 people in our trial. So probability of more than 1 is just probability of 2 plus probability of 3 plus probability of 4 all the way up to probability of 15, which is a lot, right? Like, whoa, do I want to actually compute this result? And the answer is no way, because this is going to take me a long time. I could try, it's just going to take forever. So the question now, so I'm going to put a little question here. Question: is there an easier, or I guess, an easy way to compute this? Question mark. Or an easier way. Can you guys think of anything that we could use? Well, one thing we can actually use is kind of like rule of complements, and that's going to help us. So use rule of complement. And this is a big help, because when you're dealing with problems like these, like, oh wait, this is going to take me forever, this kind of gives you an idea, like, I need to use some sort of rule. In this case, we're going to use rules of complement. So you want to ask yourself, the complement of more than 1, what is the more than 1? I guess what is the opposite of more than 1? The complement of more than 1 is less than or equal to 1. So here, more than 1, we don't include 1 in our, I guess, results. So the complement of more than 1, the opposite of more than 1, is that it's less than 1, but we also include 1. So here, the probability of more than 1 is just equal to 1 minus the probability of less than or equal to 1. And what is this going to look like? This is just going to look like 1 minus probability of 0 or 1, because less than or equal to 1 is just 1 and 0, right? And here I'm just going to put a little more work on the side. The probability of 0 or 1 is just going to be the probability of 0 plus the probability of 1. And this is a lot easier. This is a lot easier to compute than all of this. So once we computed this, we just plug it in here and just take 1 minus that value. So if you do this correctly, this is just 1 minus 0.035, which is equal to 0.965. So the probability of more than 1 is, or I guess in words, the probability that more than one person owns a tablet is 0.965 or 96.5%, which makes sense because eventually there's going to be one person that owns a tablet. So that's why the probability is so high. So just to recap, when you're dealing with problems like this where like, oh, this is going to take me forever, remember like use some of the properties of probability, like rules of complement, and then it'll cut your work significantly, like more than half. Okay, just because of time, I'll let you guys do number 4 on your own. I'm going to post the solution to this on Blackboard. Just click on the filled in notes section and it should be there. Okay, next we want to compute the mean, variance, and standard deviation of our binomial random variables. And if you kind of remember that in section 5.1, we were able to find the mean, variance, and standard deviation of random variables, but here we're taking the mean, variance, and standard deviation of binomial random variables. So they're two different things. So we compute them in different ways. So here, let x be a binomial random variables. To compute the mean here, and we call it mu of x. This is just the notation of mean. So notation is just mu of big X. So this is just the mean of X. It's just the number of trials n times the probability of success p. So n times p. To compute the variance of X, so variance of X is just sigma square X. So this is just notation of variance. Sigma square of big X. So this is just n times p times 1 minus p, where again n is just the number of trials and p is just the probability of success. And lastly, finding the standard deviation is just taking the square root of our variance. So let's do an example. The probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 25 such cars. So let x be the number that will require repairs during the warranty period. We want to find the mean and the standard deviation of x. So here, we kind of want to identify what is our p and what is our n. So here, p, our probability of success, is just 0.15. And n, a number of trial, is 25 because there's 25 such cars. So finding the mean, mu of x, is just n times p, or 25 times 0.15, which gives you 3.75. Now let's compute the standard deviation. First thing you want to do is actually compute the variance and then take the square root of it. So the variance is n times p times 1 minus p, which is equal to 25 times 0.15 times 1 minus 0.15. And if you put this in your calculator, this is going to be 3.1875 if you round to 4 decimal places. So then, finding the standard deviation is just the square root of 3.1875, which gives you 1.785. So now you computed the variance, the standard deviation, the variance, and the mean.